Once again, welcome everyone to our drone seminar series. Thank you, Amos, for setting everything up for us. Today we're just it's my distinct honor and privilege to introduce my dear friend, Muriel, Médard, professor of NEC Professor of Software Science and Engineering at MIT. And she's going to talk to us about So she's one of those people who went to MIT and never left. So I've known her for a long time, and then she's a professor there right now, and she's a foremost leader in information theory. And were you the first female president of? Second, yeah. She was the president of IEEE Information Theory Society. Yeah. Among many other things, she had too many patents for me to count. She studied many companies, and so especially if you're interested in any of the work that she's doing, please stay behind and just chat with her. She's wonderful to talk to. But for now, I'm so excited to hear about how I learned to decode.
Yes.
Okay, so here's Muriel.
Thank you very much, Peter. Thank you all for coming, especially because it's such a buzzing time around campus, and I appreciate your sharing this time with me. So today I'm going to talk about how I learned to decode. Now, as Peter very kindly introduced me, I'm an information theorist. I've been teaching information theory for more years than many of you have been on this earth. I kind of thought I knew what I was doing. And it's sort of fun at this point in your career to realize you did not know what you were doing. But not in just sort of a defeatist way, but in the happy way where you go, oh wait, there's a completely different, so much better way of doing this, okay? So that's what I'm going to talk to you about today, and particularly with the universal decoding. The work I'm going to present, all the algorithmic work is joined, and all the implementation work is joined with Ken Duffy from Northeastern University, and all of the implementation work is joined with Rabia Zizicadil from Boston University. So it's definitely very much a Boston-based little collaboration. Okay, error correction coding. We don't know what will happen to us in life, but we know we're going to make mistakes, right? That's pretty certain. And then we're going to have to fix those mistakes. Well, that is much of what we do in communications and storage. So at the top there, you have that the little drawing is supposed to look like, memory, like disks, memory disks. And the little bottom thing there is supposed to look like a little Wi-Fi router, okay? And we have sort of two different ways of dealing with mistakes, or what we call errors. One is hard detection. So there's a mistake on the disk, I read it back, and I have no way a priori of figuring out if it was likely to be a mistake or not. So in the example here, see the last bit, the 0 got turned into a 1. When I read it back, that 1 looks as reliable as all the other bits. The second version is self-detection. In self-detection, I might have something like some signal strength indicator, okay? That last bit there maybe didn't sound very loud. Maybe it was more, that means that the proportion of noise is higher. And therefore, maybe that last bit was iffy and it's red. That's my soft detection, okay? I have soft information, I have some likelihood information. And what I'd like to do is do some sort of approach where I can use a technique which will be helpful all the time, whether I'm doing hard detection or whether I'm doing self-detection. And I want to do that in a way where I can take advantage of the self-detection when I have it, but I don't have to suffer from the hard detection when that's all I've got. Okay. This is the story of information theory in a nutshell. I'm simplifying, but a lot of information theory. Let's say, 75% of information theory sort of falls into one of these buckets. I start with data, which is up there in blue. So let's say that each of these squares, I think they look a bit like chocolate squares, don't they? They look very yummy. So each of these squares is, let's say, 100 bits, okay? This is my file. It's 4 chunks of 100 bits. The first thing I'm going to do is I want to make the representation of that file as small as possible. This is called compression. I'm going to squeeze the data. Okay? It's also called source coding because it's done at the source. How many people here have ever used gzip when sending something? Okay. Oh, maybe you've received something in gzip, right? That's compression. That's squishing it, right? So you had 400 bits, and now you went down in here to 200 bits. Now, magically, you still can recover the original file. Why is that? You know, how could I go from 400 bits down to 200 bits, and I didn't lose anything? Well, it's because we have something called entropy, which we denote by H, okay? And the entropy by itself, it's just a statistic of data, like the average, the variance. It's just a statistic. Never mind what it is, it's entropy, okay? But what we can say is that if my data was squishable, compressible from 400 bits to 200 bits, it's because the entropy was no larger than a half. I'm able to squish down to, for every 2 bits, I'm able to get down to 1 bit. So the way to think about it is that even though they were 2 to the 4 potential strings, okay, 2 to the 400 potential strings, there is really only 2 to the 200 strings that I need to worry about. Okay, there were possibilities that I didn't use. So 2 to the n, where n in this case was 400, times the entropy h of s of the source s. Okay? And that's now my data, which I am going to send over a channel. Okay, so this channel, I am going to add redundancy. So I'm going from 200 bits to 300 bits. At this point, you go, Muriel, you just got rid of redundancy, and now you're adding it on. You know, how daft is that? Well, yes, that's what I'm doing. But the reason I'm doing is because the redundancy that was in the data maybe wasn't exactly the redundancy I would use to make it resilient to errors. Those errors, those bit flips where 1 becomes a 0 or 0 becomes a 1. Okay? Now, what I'm going to do is I'm going to add some redundant information to be able to recover from errors. And the errors are just deleterious effects, right? The bit flips. So for instance, maybe here I went from 200 bits to 300 bits, okay? So what's my efficiency when I go from 200 to 300? 200 over 300 is 2/3. That's a great 2/3 code, okay? That means I'm having to give up 1/3 of my transmissions with the bandwidth, the energy, all of that, all the time that's associated with that, I have to give it up to be redundant. And by the way, you know, it seems like a huge overhead. Those are the kinds of overheads that you'll have right now, for instance, in your phone. I'll show you later that that's a freaking waste, okay? But I'll show you how to do better. Okay, but that's about what we do. Now, this rate, say 2/3, you'd like to, of course, make it as high as possible while still remaining reliable. That's called capacity. And and I'll show you, it'll be very intuitive why. There's something called the coding theorem, which was developed by Shannon way back in 1948, which tells me the rate R, that rate, which is that efficiency, is upper bounded by 1. Of course, the maximum efficiency is 1, right? I don't have any redundancy. Clearly can't do any better than that. Minus the entropy of the noise. What is the noise? The noise is the bit flips, okay? Now let's think in binary, modulo 2. Let's go see Galois field of size 2. An error is adding a 1. 0 plus 1 is 1. 1 plus 1 is 0. So adding a 1 is flipping a bit. That means that my channel transmission noise is actually just like the source, something which has a statistic, which has an entropy. Now, I was using the statistics, the entropy of the source to squish it, to gzip it, for instance. What would be the world's nicest channel? It would be a very polite channel that would say, I'm so sorry. I know I'm noisy. What a pain. I don't mean to be, but I can't help it. I have noise. Tell you what, this is what I'm going to do for you. I am going to take the noise. I'm going to compress it so that it's as small as possible. And then very politely, unobtrusively, I'm going to stick it at the end. And you would say, oh, thank you so much, channel. Okay, I understand. You're a channel, you have noise. But you know, you've made my life very easy. I'll give you 8 chan of the bits to stick your noise description in there. And I'll keep, you know, 1 minus 8 chan for myself. So an 8 chan fraction will go to the noise. And the remaining fraction, 1 minus 8 chan, is my rate. It will go to me. Okay? Now, if the channel were to do this, we wouldn't be here because I wouldn't need to code. I would just not send as much data, and I would leave some space, right, for the noise. So clearly, I can do no better than that. Okay? That's basically called Fano's lemma, named after the late great Bob Fano. Okay, but that's not what's going to happen. Instead, the noise is randomly going to, you know, come and flip my bits. So I'm adding the noise modulo 2, say. So we call the input to the channel, because in information theory we're just brimming with imagination, we call it X. Yeah. And then the output, again, you know, in this with a lot of poetic license, we call it Y. All right, so X plus and the noise is equal to Y. Everybody with me so far? Okay, great. So the problem is I want to recover X from Y, but X is meshed in with the noise, and the noise has not been compressed and stuck at the end. It's all summed on top of it. Okay, how many noise strings do I have, roughly, that I should worry about? 2 to the NHN, right? Remember, same argument why I could go from 400 bits of data to a description of 200s, because they weren't 2 to the 400 possibilities, really. They were only 2 to the 200. They just happened to be spread over 400 bits. Okay? So there's 2 to the NH strings of noise that I really need to worry about. Okay. How many output strings are there? 2 to the N. All right, we can do this. 2 to the N output strings, 2 to the NHN noise strings. It means that the number of strings, if I'm able to, just in terms of like just a pigeonhole principle, just counting, if I have at most 2 to the N outputs, of course, right, and I have 2 to the NHN noises, if I'm able to get to the NR bits through error-free, it means that to the HN plus R has to be less or equal to 1, which means that R is less than 1 minus HN. That's it. Okay? That's it. That's, you know, that's your coding theorem for you. All right, so it's clear that I cannot get a rate that's larger than that. Again, you know, that's like if my noise just compressed itself and went to the bottom. Okay, it's clear that I can do no better than that. What's absolutely not clear is that I can get to that. So this is where the coding theorem comes in. This is how roughly the coding theorem was proven, you know, a long time ago. I am going to send messages to you, and I have 2 to the NR of them. Okay? Now remember, in this case, 2 to the NR is 2 to the 200, because that's the amount of data. So I have 2 to the 200 messages over here, okay? And then I have my handy-dandy Dartmouth bag, in which I have placed 2 to the 300 strings, all in lovely green. Okay, so I take my first message on a 200, I go in my bag, and I pull up a string at random. And I assign that message to that string, and I record it. I put aside the first message, I put back the string in the bag, take the next message, go in there, take the next string, and keep doing that 2 to the 200 times. Make sense? Good replacement, I know. That's, you know, that's how sloppy I am. Okay, so that's what we're going to do. And if I do that, I then have a book with all those assignments from the 2 to the 200 message to these length 300 strings, and I'm going to give it to you. I'm going to say, here it is. This is our code book. It's our way of communicating one with another. Now I'm going to send you a message. it's going to get corrupted by noise. So there's going to be +1s on some of the bits are going to flip. You're going to look at the mess, the Y that you received. You're going to go into the code book, and you're going to look over all the 2 to the 200 possibilities and look at the one that is most likely maximum probability, max I, max probability of the Y you saw, the vector Y you saw, given, so basically the maximum a posteriori, which because all of the messages are the same is also the same as the maximum likelihood. So you're going to look at the one that gives you the maximum a posteriori probability, the one message that makes it most likely that you saw what you saw. Okay? Because you know the statistics of the noise. All right. And then you will get, if your n is large enough, you will get to this r, which is as close as 1 to 1 minus hn. Okay, so why don't we do this? Okay? 2 difficulties. Difficulty 1, the storage. Remember that writing down of 2 to the 200? Not nice. Okay, so that's on my side. And then giving that code book to you. Not good. Difficulty 2. Every time you get a message, you have to go to that crazy library, that crazy code book, that dictionary, and find the one that looks the most like what you received. Also not good. Difficulty 1 actually doesn't really exist. So for instance, just to give you an idea, if I have n to be 1,000 bits, more or less, then the storage would be like 10 to the 277 strings. Not good. Turns out that doesn't really exist. Okay? We know since the end of the 1960s, beginning of the 70s, by Bob Gallagher, who was actually my doctoral advisor, we know that we can just do this with a random linear code. As a matter of fact, it's really a twist on his advisor's ideas, Médard Elias's ideas, that, you can actually use random linear codes through the compression. Remember, compression and error correction are just tightly linked. They're just kind of very, very tightly linked. Okay? So he was using matrices to shrink, Peter was. Bob was using matrices to expand, but in both cases, it's just random matrices. And what I mean by random is we're working with a finite field, and I'm literally choosing all of the elements randomly, uniformly, ID. Okay? Okay. So in that case, rather than giving you that big book, if I'm going from 200 bits to 300 bits, I give you one matrix, one, of size 2 by 300. Easy peasy. Okay? So that is not the problem. So when we talk about coding theory and you get, the coding is not, that's it. Okay, just pick a matrix at random to size 2 by 300. Really? Like, we're going to study that? The problem is actually decoding. We should call it decoding theory. Because the part that still remains difficult is the part where you have to go through the book and figure out what the heck did I send you, given that you got something that has errors. Okay. And that, a priori, for an arbitrary noise is hard. And when I say hard, it's NP-complete, and, there's some things that are NP-complete, and you kind of do them, because, like, the sizes work out, right? I mean, I don't know, I solve the knapsack problem at the, at the supermarket every week, it's not really that bad, right? Or you get pretty close or whatever. Okay, now, this was proven in the late 70s by Berlekamp, McLeese, and Van Tilburg. McLeese, late great Bob McLeese, is the author of the McLeese algorithm. How many people have heard maybe of the McLeese algorithm? But in security, yeah, all right. The security folks just gave themselves away insecurely. McLeese algorithm is one of the still standing algorithms for post-quantum crypto. So this is so hard that this is actually the basis of a lot of the post-quantum crypto that's out there, including with some of the last remaining NIST survivors. Okay, National Institute of Standards now. Okay, but so people went, oh, that's too hard. That's so hard. We're going to have to then. It's so hard that forget about these random codes. What I'm going to do is I'm going to structure my code, and I'm going to do some really clever stuff so that my code is structured enough so that I can create a decoder around that structure but maybe random enough that it looks like the random codes that, that theory told us about. Okay, and as a result, there has been a flourishing of different codes with different associated decoders. And the decoders use the structure of the code, the structure of a matrix, almost all matrix-based codes, almost all linear-based codes, to try to create these decodings that make use of the structure, while at the same time looking randomish enough that they are, getting close to the theory. So you have codes like cyclic redundancy check codes. Usually they only use, almost always, not always, they only use for detecting errors rather than correcting. Reed-Muller goes with majority logic decoding. Both Chaudhary-Hockenheim codes go with the Berlekamp-Massey approaches. CRC-aided polar codes, based on the polar codes that were developed by another student of Bob Gallagher, my friend Erdal Arakan, with a twist with CRCs. They use CRC-aided successive cancellation list decoders. We will see some of those later. Random linear codes, the ones I just told you about. Up until now, there was no decoder. Okay? And because each code had to be done with a bespoke designed decoder that was for that code, okay, because that was the case, you basically needed, that's the reason why you needed standardization. You needed a standard so that the decoder could decode the code that I sent you to correct the information that was going to get messed up by the noise. Okay? And this leads to battles royal, okay, international, highly politicized battles. And if you look at 5G, they settled on two codes for the data channel low-density parity check codes developed by Bob Gallagher as his PhD thesis, and CRC-aided polar codes, which I just told you about. Polar codes date from the late 2000s. CRC-aided polar codes date from the 2010s. Okay. Let's look again at that cycle of data that we saw before. Okay. The channel is the input plus the noise effect. Now, what Shannon had told us is do this random coding, then look at the output, look at the input, and look at how much the output looks like the input in this probabilistic way. Okay? And it's a nightmare. This is what we're going to do. So rather than identifying xn using the structure of the code, I'm going to say, I know that I don't care about the noise, but I'm going to be noise-centric. So we call this guessing random additive noise decoding. It really should be guessing random invertible noise decoding, but grand sounds good, and grind doesn't sound so good. Okay, so let's go with additive rather than invertible. But we're really just using the invertibility, nothing special about additivity. Instead of looking at the code, I'm going to identify the noise using the structure of the noise. Now remember, I have 2 to the NR possibilities for X, the thing that's transmitted, and roughly, with high probability, waving my hands, to the NH of N, so to the NH times N, H is the entropy of the noise, I drop the noise N, number of possibilities for the noise, okay? And the redundancy is the number of bits that I need to sacrifice to the noise. This is what I'm going to do. I am going to use the code only as a membership test. This means that my code book, all that glorious algebra, is going to be reduced to a hash. Okay? Now, you like to say you're a coding theorist, but if you say, what do? I build hashes, it's like, okay. All right, it's not very exciting. Okay, so we're going to use the code just as a hash, just to check. So that matrix is just going to be there to check that something is in the code book or not. Okay? So, remember, rather than looking in the book, I just have a matrix, I just check. Just like that, very quick to check. Okay? Does this match? And, of course, the input. Then the output is going to be my decoding. What am I going to do? I'm going to demodulate, so say I'm going to interpret my decoding correctly, my output correctly, and then I'm going to guess the most likely noise effect I'm then going to invert it. That's what that minus means. Okay, so my putative, my possible noise effect, I'm denoting by Z. I don't know what the noise is. I just, right? I'm going to subtract it. I'm going to invert it. If after inverting the noise effect from the output, I get a code word, I declare victory. By the way, we'll see that later. I could also keep going for a while. I could decode the most likely. I could keep going, then second most likely, and so on and so forth. This is going to be optimum. It's universal. I don't care what the codebook is. I'm just using the codebook as a hash. The complexity is not a function of the code rate, which normally in traditional decoders, the higher the code rate, typically the more work you have to do. Here I don't care. And it's going to be, and this is going to be very relevant for hardware, highly parallelizable. Okay, this is parallelizable like heck, because I can be checking multiple possibilities of noise at once. Okay, and the first one that is right, I go bingo. Okay, so we go from a pile of chips, literally, they have different chips for different codes, sometimes two different weights of the same kind of code have a separate chip. We're going to go to single chip, and we can decode all the codes. All of them, including RLCs. Up until now, we're not decodable. Just to give you an idea, see that line up there? That's capacity. That's one minus HN I told you about. The abscissa is the code length. The ordinate is the rate. Remember, high is good. And I'm telling you, if my P, my probability of a bit flip, is 10 to the minus 2, and my target Blair is block error rate. Okay, so when you talk to column theorists, they go blah, 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 Blair. Okay, it's blur, it's block error rate. We're actually trying to make sense. There are, again, this is a rich field. There are all kinds of bounds. So those two bounds that you see in blue are achievability bounds or theoretical bounds. They're ontological bounds. You don't know how to get to those bounds. The red one is actually a converse. Okay, capacity is a limit in the end goes to infinity limit. Okay, no, it's not achievable at shorter lengths. This is some bounds that are obtained from a repository that my colleague Yuri Polyansky maintains, with a nice curated set of bounds. The dots, we are obtaining by using a random linear code with grant. Okay, we are actually able to obtain it. We are able to do better than the best existing theoretical, up until now non-achievable, generally, bounds. And random linear codes exist in every length, every rate, and they don't have to be dense. You can just make them through what we call a systematic code, which means the identity matrix with a bunch of extra bits at the end to mix. That's the redundancy bit. So here's the data. So remember how I told you, the best channel out there would be the one that leaves my data alone and just gives some stuff to the noise. That's basically what we're doing here. Okay, the data alone on the left, the identity matrix, and then the stuff on the right. Okay. Yes?
So why aren't those curves monotonic?
Those curves that's because the bounds are themselves, you should actually be taking, you should be taking the whole, but that's the computation from those bounds. Again, we just took them from this repository. The dots are ours, the others are just taken from the standard repository out there. But you're absolutely right, you can take the whole. Okay, back to hard and soft detection. So hard detection is sort of maybe not as hard to see how to invert the effect of the noise. What happens when I have soft detection, when I have a more continuous effect of the noise? How am I going to subtract something that's continuous? How am I going to guess over, say, a noise in the reals, or let alone complex? All of these things are complex because, electromagnetism, there's like an amplitude and there's a phase, right? Okay. How am I going to do that? Right? It's one thing when I tell you, well, let let's get clear about what the soft detection is. The noise may be represented by a continuous value, but the effect of the noise is not continuous. Either my 0 stays a 0 or it goes to a 1. That's it. The fact that underlying it, underpinning it with something continuous, not my problem. So actually what I'm going to do is I'm going to represent that continuous noise as a likelihood ratio, as that reliability, okay? Here is a standard modulation. So again, as I told you, say electromagnetic signal, you have the reals and you have the imaginaries, right? So you have an amplitude and you have a phase. Those 4 red dots are the things that could actually be sent. This is called 4 PSK, phase shift keying, right? A shift by 90 degrees, always, counterclockwise. And that heat map is the logarithm of the likelihood ratio. How likely is it to have been a 1 versus something else? You can see I'm really certain, I'm putting in certain, maybe those hot certain things are, areas that are far away from other possibilities. When I get closer to other possibilities, my reliability, my certainty becomes very cool. It gets super, super cold when I'm right in the middle, right? Because I'm right in between 2 possibilities. So what we're going to do is we're going to take that confidence into account in figuring out how to go from most likely to least likely noise effect. Okay. Now, doing this in general can be written down. It's called soft grant, S-grant, but it's not that easy. Now, how many of you are more like computer science folks? Okay, great. So, if you're doing computer science, you like trees, but, you'll have some other structures that are pretty manageable, okay? S-grant is one of those structures that is not quite a tree, but it's pretty manageable. The reason we don't want to do it is it's actually not parallelizable. And I want to do this in hardware because we're engineers. Engineers make doohickeys that work, usually. So we want to make this parallelizable so that we can make it work. Okay? So you could use the soft information, okay, but that's not going to make our life easier. So we're going to use something else, which is called ORG-grant, ordered reliability bits. And I'm going to explain to you why. Okay, so suppose I get 500 bits, and all I do is mark the log likelihood ratio, okay? So high means I'm very certain, low means I'm not so certain. So LLR, log likelihood ratio, is the log of the fraction I'm marking now as F, because this is a probability density function, usually in Gaussian noise, but it doesn't matter so much what it is. But let's just say it's the log likelihood, so basically the log of right versus, what you chose versus what could have been the other possibility. It's a hypothesis test, 1 or 0, right? So how likely was it to be what you saw versus something else, right? That's it. So if you just empirically write them on the left, you can see they're all spread all over. Now, what am I doing on the right? I am going to take different sample paths, okay? And I am going to order them from least reliable to most reliable. Does that make sense? Okay? Just take that and rearrange it. That's all I'm doing. Literally, that's all I'm doing. And look, every time it looks like it follows a line. Now, the ones on the right don't quite follow the line, but those are the super reliable ones. That is not my problem. My problem, my bit flips are going to occur to the left. Okay? They're not going to occur at the 450th most reliable, or if it does, anyway, I can't correct it, I'm doomed. It's going to occur towards the left on the more flaky ones. Okay. If I have this order, what it means is that if it's true that the log likelihood ratio actually followed a line, once I have a line, I have a model, As a matter of fact, I don't even care what the slope is. I just care that it's a line. Okay? And again, for the computer scientists among you, particularly those of you who like combinatorics, this becomes something called the integer partition problem. Okay? Now, S-GRAN, I told you, has something that looks a bit like a tree, but it's not quite a tree. Integer partition problem, why is that nice? It's super easy to do in hardware. It's parallelizable. Bingo, that's what we wanted. So we're going to parallelize this. We're going to parallelize this. And this is what we're going to get. So in communications, apart from talking about blurs, we also talk about EB over N0. EB. EB means energy per bit. N0 is the power spectral density of the noise, usually considered to be Gaussian noise. Why Gaussian noise? Because A, we know how to manage it. B, it's worst case. C, we wave our hands around and talk about the central limit here. Okay. Energy per bit includes two aspects. One, how loud I'm being sent. Okay, so the energy that I'm sending to you. The other part is how many redundant bits I'm sending to you. So I can use energy by speaking very loudly to you or by repeating myself over and over and over again. Both of those use energy. This energy per bit takes both into account. How loud? It doesn't matter whether it's, did I use twice as much energy because I spoke once with twice the energy? Or did I use twice as much energy because I spoke at the same energy twice? This is putting all together. So the extra bits, the redundancy bits that we send for the code are like repeating, right? I mean, obviously it's smarter than repeating, but energy-wise it's the same. So that takes into account the rate. So you want your block error rate to be as low as possible. This is a log-log scale. Okay? So you can see you want your block error rate to be as low as possible, and you want your energy, EB over N0 to be also as low as possible. This is what we call waterfall curves, right? They always have this shape. Okay, so here are bits. 128, 116 means that I took 116 bits, I multiplied it by a code, which is a matrix of 116 to 128. Okay? The green over there is the state of the art with a list size of 16. Never mind what the list size is. It just means that rather than decode right away to 1, remember I told you our decoder could say, this is like one possibility, another possibility, and so on. So 16 means that the decoder would give the top 16 possibilities. The state of the art, generally, most chips do about a list size of 8. The complexity goes up exponentially. Okay, so 16 is nasty. Okay, so I'm giving a lot of, and so that's actually somewhat better than the state of the art. That's how the state of the art does with CA polar codes, which are the ones in 5G. Look how much better we do. So the EB over N0 on the bottom is logarithmic. That's called dB. dB is 10 log 10. 3 dB is multiplying by 2. 10 dB is multiplying by 10. Okay? Usually, you change standards for half a dB maybe in satellite, a full dB, sometimes less, but for sure a full dB. We're getting a full dB. Not because the code is better, but because our decoder is better, way better. Because we're optimum for any code. Now, rather than looking at all these designs of codes, let's compare other error correction codes. I have CA polar there. I have random linear code. They do about the same. I have the CRC, which is, usually only used for error detection, but is super, super, super simple to check. They're built to be simple to check. That's actually the best, the CRC. I have polar-assisted convolutional codes, which are like the latest, greatest. They're just the same as others. I can even use AES, which is an encryption algorithm, which is nonlinear, which was never even meant to be error correction. Remember how at the beginning I said, the nicest channel out there would just put its bits compressed of the noise at the end? What if I have to pad in AES anyway, right? crypto people here, they know you have to pad, right? So I'm going to use the pad, and I'm going to use that as the space for the noise. It does the same. All the codes do roughly the same. And you can see that with 116 to 128, 112 to 128. Sometimes people say, well, what if you use machine learning? Okay. Hey, I love machine learning. Every so often I teach it. Okay, so let's start with that. But here, no. Okay? Now, this is not my saying it. This is a group from Baatsoek Steaming in the Netherlands. So you see random codes using Overgrand. So first of all, for the decoder, forget it, because we already have an optimum decoder, right? The question is, could I build better codes? And you can see there they're using the state-of-the-art machine learning approaches to building codes compared to random. You would not get out of bed for that. Okay? Okay. Here are the chips we have made. The one on the left is for hard detection. The one on the right is for soft detection. The soft detection one we presented to ISSCC this year with a demo. How much better do we do with our universal decoder over the state-of-the-art decoders? So here again, log, throughput on the abscissa, on the ordinate energy per bit, picojoules per bit. So this is energy, these are joules, okay? So throughput energy, obviously the diagonal of power in milliwatts. We are by far the lowest power. We're also the lowest picojoules per bit. Now, the little drawings, the little icons that are full are actual chips, doohickeys, okay? The ones that are not filled out are synthesis results. So there's a couple of groups, particularly a group from Gross at University at McGill that has taken our algorithms and implemented them and in synthesis and that's what they get. Okay, that's what they get. So usually synthesis does much better than implementation because in synthesis, your clock doesn't slip. You don't have parasitic currents doing nasty things to you, not much, right? So we are able to, so we're basically 17 times better than the state of the art. Now the ones on the left are all for dedicated. Why do we do better than the folks on the right? And this is going to be, if you will, a philosophical plea. Algorithmic people, theory people, work with the circuit designers. It's because we work together. Right? The other team basically took our algorithms and just implemented them. And by just, I don't mean to be dismissive, but did it just only that. Just to give you an idea, so they actually ordered all the bits. Remember how we were talking about ordering the bits? It ordered all the bits and then did our, the whole manipulation with the integer partition problem. We didn't order all the bits. As we went ordering the bits, we started doing the integer partition problem, which means that very often we stopped way ahead of time. We didn't have to, we only did work we needed to do because we really understand the algorithm and because we knew that how the implementation was happening in the circuits. So really that working together, huge difference. Okay, huge difference. It's a factor of at least 5, because remember, if you actually went to implement it, the synthesis is never going to work as well. It's always going to work much better than the implementation. Okay, so this is what we've done. So you can see just a comparison, much lower picojoules per bit. So we broke the picojoule per bit barrier. Yeah, and it feels good. All right. How many trials are we doing in order to get to our decoding? And how much does it matter about the code? It doesn't really matter about the code. Okay, this is statistical. Okay, this is basically geometric. How many trials you have to do? It's a Bernoulli process. It's like flipping a coin. It's so much easier than looking at the code and doing all kinds of horrible bounds with complicated names. That's it. There's an NK code. So I had K bits. I turn them into N bits. K has to be less than NR. That means it's 2 to the K minus 1 erroneous decoding. If the code book was chosen at random, the likelihood a code book query would identify a code book is 2 to the K over 2 to the N. That's it. Which is giving me 2 to the minus N minus K. Okay? You could have done this as, first year, second year undergrad. So number of queries until an erroneous decoding is geometrically distributed with approximately 2 to the N minus K. Now, never mind the formula at the bottom. I'm just going to say it's not bad. It may look bad, but trust me, in this area, that's not bad. Okay? But look at the top. I can now be remember, I'm using the likelihood at the inputs. But now my outputs, I have a lot of statistical information about the reliability of my outputs, the probability that a decoding is correct. Once I give you the decoding, how certain am I about that decoding? What's the probability that you found the correct noise effect? Remember that you're inverting. And it's over the probability that A, the noise effect was found, plus the probability that you found the incorrect thing. What does this mean? It means that for physical layer security, which relies on transmitting at a rate which is above capacity, beyond that 1 minus R, for the eavesdropper, there's my eavesdropper, see, looks very shady. So normally, you can transmit at a rate which, would be below capacity. And there's something else called the min capacity. So below capacity, you're like, well, maybe if my N is large enough at min capacity, the traditional sort of folk theorem is like, no way they can, the eavesdropper can figure out anything if you transmit below min capacity. The success probability versus the bit flip you see here, because we have this universal decoder, unless your N is really at infinity, we're able to break it. So we're able to break systems, which is also fun, okay? Let's face it, okay? So breaking records is fun. Breaking systems, also a lot of fun. Just to give you an idea here, these are sort of state-of-the-art physical layer codes called random read Mueller coset codes. Never mind what they are. They just, they even sound scary, right? I mean, you wouldn't want to meet one of those late at night in an alley, right? And what you see here is the over N0 success probability. Now, what's happening here? Eve is going to guess, and if she doesn't guess quickly, Eve the eavesdropper, if she doesn't guess quickly, she just goes, forget about it. Forget about it. So most of the time she's like, I'm not even going to try to decode this thing. But every so often she gets lucky, and then when she gets lucky, she's super sure that her decoding was good. So she's able to get a probability, say around a few % of decoding, and on top of that, when she decodes, she's like 60% sure that what she decoded was correct. This is not a good security system. So that's been a fun thing. And of course, I showed you we have the chips, so we can do this. Okay. I told you about LDPCs for data. So LDPCs are long codes. They're long, like 1,000 or more bits, versus the things I showed you, which were around 100 bits. Now, it's not that Grand by itself cannot do better, but remember this argument here with the N minus K. I can have a large N, I can have a large K. My N minus K for straight up Grand can't be too large. 20s, 30s, right? Now, it's not about rate, it's not about length, it's about the number of redundancy bits. But if I'm going to have a rate 1/2 code when the code is super long, like 1,000, 2,000, and I'm going to go to rate 1/2, now my N minus K is no longer 20s, 30s, it's like 1,000. right? And I don't want to have to do to the 1,000 guesses. So I told you about Elias, who was Gallagher's, so it's like my, research grandfather. One of the things he did, other than create these great random codes for compression, is he did these things called product codes. Product codes have been around since the 50s, okay? And basically what you do is you create a code where you have codes that run horizontally and codes that run vertically, okay? And that's it. That's a product code. Okay, so you have the check bits horizontally, and you have the check bits vertically, and then you have a few check bits in the corner that, you massage, we can talk about it later. But that's it. Now, these codes have been around forever, and they have been considered to be not very great codes. Now, funny enough, you can prove that they're capacity achieving. Because remember, random codes are capacity achieving. Most stuff is capacity achieving, okay? So, but they were considered not to be so good. Lots of fantastic work on it, which I referenced down there. And then you could use Grand as the component decoder. Okay, and we did that. And we actually demonstrated with the chip. But let's go back to what I told you here about this reliability. These are very recent results that, which is going to appear in GLOCOM 2023. If you use this reliability in updating your belief as you so how do decoders work in these products? You decode horizontally, then you fix things, you decode vertically, you go back to decoding horizontally, back and forth, back and forth. It's like when you solve a crossword puzzle, right? You try to do the horizontals, you then try to fill them out with the verticals, you go back and forth, right? You do what you can. Okay. Remember, EB over N0 in dB, right, 10 log 10, block error rate. This has never been shown before, okay? I was hesitating to show it, but this is world premiere. In blue, you see the 5G LDPC with a maximum number of iterations, back and forth, with the normalized min sum, sort of the state-of-the-art for low-density parity check codes, using something called belief propagation, never mind what that is. Okay. In black, an LDPC with an optimum belief propagation with 50 iterations. In red, the Duffy et al., so that's what we've been doing, with list size of 4, so max of 20 iterations. I'm not even showing you 20 iterations for the belief propagation because it's risibly lousy, okay? 2 different parameters, never mind how we choose them. We do better. So these codes that have caused, consternation, major discussions, often not even that polite, okay? In standards bodies, the LDPCs are they're just another code. They're not even that great, okay? And on the right, you see, so on the left is for a code of length 625 with, very low rate because it's 225 bits of information for 625 output. Okay? So it's, just about like a third. Very low rate. So it's like, 400 bits of redundancy that you wouldn't do to the 400. On the right, it's length 484, again, very low rate. And you can see we do better. These are the world's simplest, most rudimentary, most unimpressive codes. Okay, you know what? I'm going to stop there, just tell you that we can do much better with all kinds of stuff. I'm going to encourage you to look at our webpage. And with that, I shall take questions over the last couple of minutes.